Okay, today we're going to talk about the properties of water. Of water. Let me use this instead. Water. Okay. Um, when we look at water, we know that this is H2O. Okay, we know that this comes from water is in group 16, or sorry, oxygen's in group 16, and we know that hydrogen is in group 1, and so this has 6, hydrogen has 1, and so this is what we call it. We're going to share the electrons here. So this has 2, this has 2, and this one now has 8. And so this is what we're going to call, this is a covalent, if you guys remember, bond. Okay, they're sharing. However, we have these two lone pairs. So you see a lone pair here and a lone pair here. What happens is this causes an unequal sharing of electrons, and this oxygen is more electronegative. And so what happens, we get what's called a dipole, and the dipole adds this way. So we have these two sets of lone pairs of electrons, okay? And so what happens is, because oxygen wants the electrons closer to it, it actually pulls these two electrons away from the hydrogen and closer to itself. And this is why water is unique, because it pulls these electrons close. This end of water has a partial negative, and this has a partial positive, and a partial positive. So what happens is, water, you've got these two partial negatives, and you've got a partial positive here and a partial positive here. So water is going to act, so water acts as a magnet. So when you have a bunch of water molecules, what's going to happen is they're going to hydrogen bond with each other. And if you guys remember, you can only hydrogen bond when you have an H bonded to an F, an O, or an N. So what happens is, this negative part of the oxygen, of the water molecule there, the oxygen, it's going to interact there, and then we're going to have another water molecule that's going to interact here. And so you can see that water ends up making this network, okay? Because again, remember, this is going to be a partial positive, and here you've got a partial negative, and then here you've got a partial positive, so that basically it's going to end up looking like this is a network that you have here. And so your oxygen is always going to have an interaction with your hydrogen here, because this is partial positive and this is partial negative. So this is what we call hydrogen bonding. Okay, we say this is your partial positive. Okay, so it looks like this. That's the symbol for it. And this is because oxygen pulls the electrons away from it. And then you also have, on water, you have your partial negative. So it looks like that. Okay, so this is why water acts the way it does. This is why, okay, so if we look at water, the reason water has a high boiling point, so this is has a high boiling point. And the reason that water has a high boiling point of about 100 degrees C is because it doesn't want to, the molecules want to attach to each other. They want to interact with each other, and so it's hard to break these hydrogen bond interactions. And so what you see with an alcohol, let me draw you the structure of an alcohol. If we have methanol, so this is going to be a methanol here. You see we have an OH bond here, and so this again is going to have the partial negative charge, and this is going to be your partial positive. So anytime you have an OH bond, you should get this. Well, what happens is, this can bond or have an interaction with another alcohol. So you see this interaction here. But you see the CH group that we have here? This doesn't interact with anything, because this hydrogens here are next to a carbon. So there's no hydrogen bonding with this part. We can only hydrogen bond here. And so there's parts of this that aren't hydrogen bonding, and so this is going to have a boiling point, so we say BP for boiling point, of about 78 degrees Celsius. So this boiling point for alcohol is going to be lower than your boiling point for water. And it's because water has more hydrogen bond interactions, less here when you look at your alcohol. Hopefully that makes some sense to you. Okay. So when we look at water, okay, so water looks like this, right? You've got your partial negative here and you've got your partial positives. Water is going to dissolve ionic compounds. So the question is, why is water able to dissolve these ionic compounds? Okay, the reason is because if you have something like sodium chloride, okay, when you put this into water, it breaks up into Na plus and Cl minus, and the water molecules actually surround this. So all the negative ends, this is your partial negative, right? Negative, sorry, are going to surround the positive sodium ion. Okay, so we get this. And then your positive end of water, they're going to surround the negative end of your chlorine. So this is why you're going to have, this is why you end up being able to dissolve ionic compounds in water, okay? If we look at something like the structure of an oil, so your structures of oil, they have a bunch of CHs. And these aren't going to, so if you think about this, when you put baby oil on your hand and then you try to put water on it to wash it off, you can't wash off the baby oil, right? It just beads up. The reason is because you've got this structure here. These hydrogens here, because they're attached to a carbon, they cannot hydrogen bond with the water. And so basically, they end up staying by themselves, and water can't surround these. So that's why you get in salad dressings, you have this, if I have like, if this is a test tube, you know, I might have the oil here, right? And then you would have your water here, but you would see that separation, okay? So, and again, that's because this can't hydrogen bond. So if I have something like the structure of a sugar, so your structures, your sugars, they have these OHs on them, okay? And so because these sugars have these OHs, you can hydrogen bond. And so the rule that we have is, it's called like dissolves like. So in order for something to be soluble in water, it has to be similar to water, and it has to be similar in structure. So if water, we say, is polar covalent, and again, polar covalent because it has unequal sharing. So water is going to have the partial positive and the partial negative, right? Anything that's got a partial positive and a partial negative will be soluble in water. Anything that has a full positive and a full negative will also be soluble in water. So this also means that most of your ionic compounds will dissolve in water. Okay? All right. So now when we dissolve things in water, there's a couple of definitions you need to know. You need to know solvent, you need to know solute, and you need to know solution. Okay. So the solvent is what you use to dissolve the solute. Okay. So in this case, if we're trying to make a solution of, let's say it's a salt solution, okay, your solvent is water, okay, and your solute is NaCl. So your solute is what you are dissolving. Does that make sense? I hope it does. Okay, so those are the definitions that you need there. And the last thing that we want to talk about, we talked about boiling point. Let's talk about surface tension. So surface tension. Got a demo here for you. So I have a penny here, and I'm going to put water on it. So think about how many drops of water that you think you can put on this penny. Okay, some people I've heard say 10, 20. You can put about, let's see, there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. What you guys can start to see, hopefully you can see this with this. Let me move this a little bit. The water is actually, I don't know if you can see that. The water is actually going to start hanging over the edge of the penny. So you can see how this is getting bigger and bigger. Okay, and it finally spilled over, right? The reason that water is able to spill over to the side of the edge, or sorry, over the edge of the penny, is because of what we call surface tension, okay? And so surface tension, basically, you've got your penny here, and we put the water on it so that the water actually formed a bubble over this. And the reason is because all these water molecules, they want to stick together as much as possible. And so this is what surface tension is. It's also the same thing that you see the Jesus lizard, the lizard that can run on the water and stuff like that, is because the water forms, basically it's like this skin right here, and it's hard to break this skin. Once you break the skin, like we did over here with the penny, the water's going to spill over. Surface tension is just a matter of the water molecules want to stick to each other. And so because they stick to each other, it can actually bubble out and form this. The only other thing when you talk about freezing point. Okay, so with your freezing point, what happens to, and this freezing point is going to go along with a little bit of what we talk about with density. So when we talk about this, why does ice float? Okay, and the reason ice is going to float is because it is less dense. And you guys should figure this out when we go through the lab, when we talk about what's going on with the actual water molecules in here. But you get something like your water molecules are going to sit next to each other, and you can see if I put another water molecule right here, okay, the closer these get, now you're going to start to have an interaction with these negative ends here, right? Or if I put another oxygen here, what now happens here? We get, this is what we call repulsion, okay? So this is repulsion. Repulsion. Oh, I don't know if I spelled it right. Anyway, this is repulsion. And what's going to happen is these are both have a positive charge, right? These both have this partial positive. And so once they get too close to each other, what are they going to do? They're going to actually push apart. And so when your water starts to freeze, the molecules, remember, there's this average kinetic energy, and the molecules are going fast and fast and fast, right? And then all of a sudden they start to slow down, they slow down. They get to where they're almost stop moving, because in a solid we know that there's only slight vibrations. And so as these get close to each other and they get slow down, they get too close and they push apart just a little bit. So ice is actually, so the density of it, ice is less dense because the water molecules are just a little bit further apart because of this repulsion. So that's why ice is actually going to float, because it's less dense. Okay, I think that's it for now. Come back and check the channel for the next couple of questions, or sorry, the next couple of lectures.